For almost a decade, the architecture inside our biggest AI models has really been built on one simple, sturdy idea. But, what happens when that sturdy design actually becomes a bottleneck? Well, today we're diving into a new paper about something called Manifold-Constrained Hyper-Connections, or mHC. And trust me, it's a total rethink of the information superhighways inside these neural networks. The whole point is to make them wider, faster, and, this is the most important part, completely crash-proof. So let's get into it.
So, here's how we're going to break this down. First, we'll look at the current standard, what I'm calling the reliable but kind of limited one-lane highway of AI. Then, we're going to talk about the big attempt to build a bigger highway and, well, the catastrophic crashes that happen next. After that, we'll unpack the super elegant mathematical guardrail that actually fixed it, and we'll reveal the surprising, 1960s algorithm that makes it all work. And finally, we'll explore what this new way of scaling things really means for the future of AI.
All right, let's start at the beginning with the one-lane highway. To really appreciate how big of a deal this new thing is, you first have to understand the foundation that's been powering deep learning for years and years.
The modern era of deep learning really just ignited with one simple but honestly brilliant idea: the residual connection. This was introduced with ResNet way back in 2016, and it basically acts like a bypass, letting information from the start of the network skip way ahead to much later layers. This direct path is what prevents the signal from just fading away, from vanishing or exploding, and that is the key that let us build models that are hundreds, even thousands of layers deep.
The absolute best way to think about this is like a single-lane highway. Information gets on at the beginning, travels this direct path right alongside all the complex stuff happening in the other layers, and then it exits at the end. It's super reliable. But you can probably guess the problem as models get bigger, right? Every single kind of information, syntax, grammar, logic, what have you, it's all forced to compete for space on this one tiny road. It's a huge bottleneck.
Which brings us right to our next section: more lanes, more problems. I mean, the obvious solution to a traffic jam is just to add more lanes, right? But in the world of neural networks, that ambition led to an inevitable and pretty catastrophic crash. So the intuitive next step was this idea of hyperconnections, or HC. And the idea was brilliant, really. Instead of one residual stream, why not have 4 or 8? The model creates multiple parallel lanes and then uses these special matrices to let information mix and move between them. In theory, this gives the model so much more room to think without adding a ton of computational cost. It's like going from a country road to a multi-lane superhighway. But there was a catch, a really fatal flaw that only showed up when you tried to scale it. Once you stacked about 60 of these hyperconnected layers, the entire system would just break. Training would become completely unstable. You'd see these sudden, massive spikes in the loss, gradients exploding. The shiny new superhighway was causing these massive digital pileups.
So what was going on under the hood? Well, this uncontrolled mixing between all the new lanes was actually amplifying the signal as it passed through the network. And we're not talking a small amplification. The research found that the signal's energy could get amplified by up to 3,000 times. That is not a typo. A 3,000x gain. Training was just impossible. And what's so important to get here is how this problem just compounds on itself. I mean, one layer might only amplify the signal by a tiny, tiny bit. But when you do that 60 times in a row, you're multiplying those gains over and over and over. This chart shows you exactly what happens. The signal for a standard model stays nice and flat, totally stable. But for hyperconnections, it just grows exponentially right off the chart. That's pretty much the textbook definition of training instability. Okay, so we have this really powerful idea for a superhighway, but it's dangerously unstable. This leads us to the core innovation here, the mathematical guardrail. This is the elegant fix that finally makes the superhighway safe to drive on. The solution is to put a very specific rule on those mixing matrices. They have to be what's known as a doubly stochastic matrix. Now, I know that sounds super intimidating, but the rules are actually surprisingly simple. First, all the numbers inside the matrix have to be positive or 0. And second, every single row and every single column has to add up to exactly 1. That's it. This constraint basically forces a perfectly fair mix of all the signals.
The researchers use a fantastic analogy for this. Think about an audio mixer. A normal, unconstrained matrix is like a volume knob you can just crank up to infinity. But a doubly stochastic matrix, that's like a perfectly balanced mixer.
The total signal energy that comes out is guaranteed to be the exact same as the total energy that went in. You could chain 1,000 of these things together, and the volume would never explode or fade away to nothing. It perfectly conserves the energy of the signal. So why is this one little constraint so powerful? Well, it all comes down to two really beautiful mathematical properties. First, a matrix like this simply cannot amplify a signal. Its amplification factor is never more than 1, so no explosions. Second, and this is the real secret sauce, if you multiply two of these special matrices together, the result is another one of them. This property, it's called closure under multiplication, is basically a mathematical guarantee of stability, no matter how ridiculously deep your network is. So we have this perfect mathematical guardrail. But how do you actually force the network's matrices to follow these rules while it's training? Well, the answer, incredibly, comes from a 50-year-old algorithm making a pretty spectacular comeback.
I mean, this timeline really puts it all in perspective. We got ResNets in 2016, then the unstable hyperconnections in 2024. And the key that makes the stable mHC version actually work? An algorithm called Sinkhorn-Knopp, first published way back in 1967. It's just wild that a piece of math from over 50 years ago is the missing piece for this next-gen AI architecture.
And the algorithm itself is beautifully simple. You basically just take any matrix and you nudge it into shape over and over again. First, you make sure all the numbers are positive. Then you force all the rows to add up to 1. Of course, that's going to mess up your column sums. So next, you force all the columns to add up to 1. Now your rows are all messed up again. But here's the magic. You just keep repeating that process, back and forth, rows, then columns, and it is mathematically guaranteed to quickly settle into that perfect, stable state. Okay, so let's get to the payoff. Now that we have a stable, multi-lane superhighway for our AI, what does that actually get us? What's the bottom line in terms of performance and efficiency?
And this is where it gets really impressive. This constraint isn't just a safety rail. It actually boosts the model's performance. The data here from a 27 billion parameter model shows that mHC consistently beats both the standard baseline and the unstable hyperconnection model on all these major benchmarks. So you're not trading performance for stability. You're actually getting more of both. It's a win-win.
Now, the obvious question is, what's the catch? What's the cost? I mean, running that old school algorithm over and over sounds like it would be computationally expensive. But through some really clever systems engineering, like something called kernel fusion on the GPU, the team got the total training overhead down to just 6.7%. For this kind of stability and this kind of performance leap, that is an incredible bargain. So, the big picture here is it's really profound. For years, we've had two main levers to make AI models better. You either make them deeper by adding more layers, or you make them wider with more parameters. This work introduces a genuine third axis for scaling, connectivity. We can now actually engineer models with richer, more complex internal information highways, and that could unlock new capabilities in a much more efficient way. Which leaves us with a pretty fascinating question to think about. We've just seen the journey from a single-lane road to a crash-proof superhighway for information inside an AI. So now that we can safely scale models along this new axis of connectivity, what new kinds of reasoning or creativity or what emergent abilities might that finally unlock? It really does open up a thrilling new frontier for how we build AI.